In the last video, we talked about pressure on an arbitrary slice of fluid. Okay, so in this particular video, we're going to go into Pascal's law. The idea here is that we have an arbitrary cube of fluid that we're going to analyze. So the way we're going to analyze this is we are going to have a reference point, and at that reference point, there's going to be a force that acts upward. All right, and we know that force, but that force is going to be P initial times A, and that's coming from our definition of pressure. So P initial is our reference point pressure. A is the area of that square at the bottom. So it should be pretty much the same everywhere. Okay, and then this fluid has a weight that's going down. We'll call that W. Okay, and we also have a pressure on the top. Okay, so that pressure on the top is going to be called PA, or the force that's on the top. So now we're going to go, let's just take that cube directly out of this particular fluid so we can analyze it a little bit better. All I'm doing is just erasing the jar around it because the container around it, we don't necessarily need it. I think you guys get the picture. Let me just pull this back on up here because I erased too much. All right. So we have ourselves this jar here, or not this jar, but this arbitrary piece of fluid. And of course, fluid, this type of fluid is a liquid, and it's not necessarily going to hang in air like this. So we're just going to analyze it from this perspective. Now, this is what I want you guys to remember. Remember that we have Newton's second law, no, it's his first law, and that is going to be the net force is going to equal to 0. So this thing shouldn't be moving. So this implies that the net force, well, since we see all of our forces there, this equation is going to imply that the force on the bottom, and I'll just call this FO, is just going to be FO minus PA minus the weight, and all of this is going to equal to 0. So let's make sure that we go ahead and define this height. Let's call this H initial, and let's call this just some H. Okay, so that means that if H initial is 0, that means that our height is just, or this is just H. If we define H sub 0 as 0. So let's just continue right on. So we can go ahead and pull this pressure initial, or pressure at our reference point, times A minus pressure times A minus the weight of the fluid, and that's just going to be M times G equals to 0. So we know the area, we know the height, so we're going to go ahead and break this down even further. And I'm just going to pop a new page up here. Remember, P initial times A, and I don't want to call it P initial, I want to call it the reference height, minus P, and this is the height, this is the top of the fluid right now, this cube of water outside, and this times A, minus M times G equals to 0. Remember that density was just equal to mass over volume. Well, this is going to imply that mass is going to equal to rho times volume. But volume, if you remember, for a cube, is just length times width times height. So the length times the width is the area. And then we have our height. And so height times the area is going to give us our volume. Okay, so we can substitute this back into our mass equation. This implies that mass is going to equal to area times height. And this implies that mass is going to be rho times our area times our height. So this implies that mg is just going to end up being rho g h a. So we're going to substitute that back into our original equation up here. And all this is equal to 0. So I want you to notice that the area is going to be the same all the way through, so we can just take that out. We can divide one side by A. Divide one side by A, so we divide this side by A, and we'll divide this side by A. So this is going to end up being P initial minus P minus rho G H all equals to 0. The A's cancel, or over 1, and then 0 over A is just 0. Okay, so this is, we're going to continue right on, and I'm just going to say that the pressure at the reference point is going to be equal to P plus rho G H. So to me this makes sense, because if you put water on top of my head and then put some oil on top of the water, then or put some more pressure on top. So the pressure from the oil plus the pressure of the water, which is what this is saying to me, is going to equal to the total pressure at the reference point. So if we go back here, what we're saying is this is our reference point right here. All right, HO. And if we're just considering this pressure here plus the fluid here, then this is how we can relate the pressure at that reference point to what's happening over our head. And so all we're doing is adding pressures up. To me, it's simple when I think about it in terms of Newton's laws. We're adding things up. Okay. This is Pascal's law. We will, let me just round this off a little bit by giving you a definition. It says Pascal's law. Pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls containing to the walls of a containing vessel. The pressure depends only on depth. The shape of the container does not matter. So I want to go into that a little bit more in the next video. You know what? I'll go into it in this. Now, the next video.